From nebula to supernova. In the deepest regions of space, far beyond the reach of human imagination, the universe is in constant motion, even when it appears completely still. What we perceive as silence and emptiness is actually a vast, dynamic ocean of energy, gas and dust, where time stretches across billions of years and where the most powerful processes in nature unfold without interruption. Among these processes, one stands above all in both beauty and destruction: the life cycle of a star. Every star you see in the night sky is not a permanent object, but a living system, born from chaos, shaped by gravity, sustained by nuclear fire, and eventually destroyed in an event so powerful it briefly outshines entire galaxies. This is the continuous journey from nebula to supernova. Everything begins within a nebula, an enormous interstellar cloud composed mainly of hydrogen, helium, and trace amounts of heavier elements and cosmic dust. These clouds are not uniform. They are shaped by turbulence, shock waves from ancient stellar explosions, and the subtle but relentless pull of gravity. Over immense spans of time, regions within the nebula begin to collapse under their own weight. Nothing triggers this collapse in a single moment. Instead, it is the result of gradual instability. A nearby supernova might compress parts of the cloud, or random density fluctuations may slowly grow until gravity takes over completely. As the gas contracts, it fragments into denser clumps, each one becoming a potential birthplace of a star. Within one of these collapsing regions, pressure and temperature steadily increase. The cloud, once cold and diffuse, begins to heat as gravitational energy is converted into thermal energy. At the center of this collapsing mass, matter gathers more rapidly, forming a dense core surrounded by a spinning disk of gas. The system is still not a star in the true sense, but a protostar is emerging. It does not yet produce energy through nuclear fusion. Instead, it glows faintly due to heat generated by compression. The environment is violent and chaotic, with jets of gas being ejected from the poles of the forming object as magnetic fields interact with infalling material. As the protostar continues to accumulate mass, its core temperature rises dramatically. When it reaches approximately 10 million degrees Kelvin, a critical threshold is crossed. Hydrogen nuclei begin to fuse into helium through nuclear fusion, releasing enormous amounts of energy. This marks the true birth of a star. At this moment, a balance is established that will define the star's existence for most of its life. The inward force of gravity, which seeks to collapse the star further, is counteracted by the outward pressure generated by nuclear fusion in the core. This state of equilibrium is what we call the main sequence phase. During the main sequence, the star enters a long period of stability. Energy produced in the core slowly makes its way outward, taking thousands to millions of years to reach the surface, where it is emitted as light and heat. The characteristics of the star, its color, brightness, and lifespan, are determined primarily by its mass. Smaller stars burn their fuel slowly and can remain stable for tens or even hundreds of billions of years. Larger stars, however, consume their nuclear fuel at an astonishing rate, shining intensely but living comparatively short lives. Even though these stars appear unchanging on human timescales, within them, hydrogen atoms are continuously being fused into helium in a process that defines their existence. Eventually, the hydrogen in the core begins to deplete. When this happens, the delicate balance that has sustained the star begins to shift. Without sufficient hydrogen fusion in the core, the outward pressure decreases and gravity starts to compress the core once again. As the core contracts, it heats up, allowing hydrogen fusion to continue in a shell surrounding it. Meanwhile, the outer layers of the star expand significantly. The star transforms into a red giant, or, in the case of more massive stars, a red supergiant. Its radius can grow so large that if placed in our solar system, it would engulf the inner planets. Inside this expanded structure, new fusion processes begin. Helium atoms fuse into carbon and oxygen, and in more massive stars, successive stages of fusion create progressively heavier elements such as neon, magnesium, silicon, and eventually iron. Each stage of fusion requires higher temperatures and occurs over shorter timescales than the previous one. The star, once a stable engine of hydrogen fusion, becomes a layered structure resembling an onion, with different elements fusing in concentric shells around an iron-rich core. But iron represents a turning point in the life of a star. Unlike lighter elements, iron does not release energy through fusion. Instead, it consumes energy. As iron accumulates in the core, the star approaches its inevitable fate. In massive stars, once the iron core reaches a critical mass, it can no longer support itself against gravitational collapse. Without the outward pressure generated by fusion, gravity takes over completely. In a fraction of a second, the core collapses at a significant fraction of the speed of light. Protons and electrons are crushed together to form neutrons, and the core becomes incredibly dense, forming either a neutron star or, if the mass is sufficient, a black hole. The collapse of the core triggers one of the most violent events in the universe. The outer layers, no longer supported by the core, fall inward and then rebound outward in a catastrophic explosion known as a supernova. A supernova is not merely an explosion, it is a cosmic event of unimaginable energy. In a matter of seconds, it releases more energy than the sun will emit over its entire lifetime. The shockwave generated by the core collapse propagates through the outer layers of the star, tearing them apart and ejecting them into space at speeds reaching tens of thousands of kilometers per second. For a brief period, the dying star can outshine an entire galaxy, visible across vast cosmic distances. This explosion is not just destructive, it is also creative. Within the extreme conditions of a supernova, elements heavier than iron are formed, including gold, silver, uranium, and many others. These elements are then scattered across space, enriching the interstellar medium. The remnants of the core that survive the explosion become either a neutron star or a black hole. A neutron star is one of the densest known objects in the universe, composed almost entirely of neutrons packed together so tightly that a sugar cube-sized amount of its material would weigh billions of tons on Earth. Some neutron stars emit beams of radiation from their magnetic poles, and as they rotate, these beams sweep across space like cosmic lighthouses, creating what we observe as pulsars. If the remaining core is even more massive, collapse continues beyond the neutron star stage, forming a black hole, a region where space-time is curved so intensely that nothing, not even light, can escape its gravitational pull. Yet, even in destruction, there is continuation. The material expelled by supernovae does not disappear. It spreads into surrounding space, mixing with existing gas and dust, forming new nebulae. Over time, gravity begins the process anew. These enriched clouds collapse, forming new generations of stars and planetary systems. Each cycle of stellar birth and death contributes to the chemical evolution of the universe. The carbon in living organisms, the oxygen we breathe, The calcium in our bones and the iron in our blood were all forged in the hearts of ancient stars and distributed across space by supernova explosions. In this endless cycle, the universe continuously transforms itself. Stars are not isolated objects, but essential participants in a cosmic ecosystem of creation and destruction. From the quiet, almost imperceptible collapse of gas in a nebula to the final brilliant explosion of a supernova, each stage is part of a single uninterrupted process that has shaped the universe for billions of years and will continue long into the future. What we observe as individual events are merely phases of a greater continuum, one that connects all matter in the universe through time, gravity, and nuclear fire. In the end, every star tells the same story in different ways. It is a story of balance and imbalance, of creation and destruction, of beginnings that arise from ancient remnants and endings that give birth to new beginnings. And as the universe expands and evolves, this cycle continues without pause, written across the sky in light that has traveled for millions or even billions of years to reach us. When we look into the night sky, we are not simply seeing distant points of light. We are witnessing the ongoing history of the universe itself, unfolding without beginning or end, from nebula to supernova and back again.